Hey programmers, I'm Alvin from CoderByte, and today I want to teach you about the linked list data structure. Linked lists are a really important data structure to study because they're actually used as components of more advanced data structures like stacks, queues, and even hash tables. And because of this, they're a pretty common topic when it comes to your software engineering algorithm interviews. So our objective for today is to, of course, build a simple linked list that supports a few basic operations. Mainly, I want to implement a linked list that can add a new value into the list, as well as print all the values in the list, and also search for an existing value of that list. I think one of the best ways we can learn a new data structure deeply is to, of course, build it from scratch, so that'll be our goal for today. Before we jump into implementing our linked list, let's go ahead and cover some background information. So what's so special about a linked list compared to other data structures? Well, the first thing we'll need to recognize is just in its name, right? A linked list has a very particular structure where the values that we're storing are chained together sequentially. That means one value is basically linked to the next value. This chain structure actually gives us some noticeable advantages when we compare that to other data structures. Mainly, linked lists are going to be pretty efficient when it comes to insertion and deletion compared to other data structures like arrays. Another cool advantage of linked lists is how they're stored in memory. What we say is that linked lists don't require contiguous memory to be stored. Here what we're saying is that when you store a linked list in your computer's memory, it actually is not required that those memory addresses are next to each other. With that last point in mind, let's actually visualize this memory. So here I have a neat little diagram of how your computer's memory will store things like arrays as well as linked lists. So the first thing I should mention is, of course, this is a simplified diagram, so for all of my computer architects in the crowd, you're just going to have to bear with me. But I think this illustration does a great job of actually visualizing the key difference between array memory as well as linked list memory. So let's begin with my array example. Let's say I wrote a program that declared an array of 4 elements, A, B, C, D. What I have drawn here is a depiction of how that data is actually stored in memory. So this is kind of different blocks of memory I have drawn. And what you'll notice is each block has an address. Here I just simplified the addresses. They just represent some numbers, right? So this has address 7, this has address 8, this has address 9, and so on. What you'll notice is we have each element, being stored at some address, but more importantly, the elements are stored at consecutive or contiguous addresses, right? So I know that A is going to be the first address of my array, B is going to be in the next largest address, and so on. So a key thing to understand right now is when it comes to our arrays, those elements are stored at contiguous memory addresses. And the upshot of that is it's really quick to access particular indices or positions of this array. It's all a matter of just some simple arithmetic, right? If I memorize the starting address of my array and I want to hop to, let's say, the 4th position, I can just basically add 4 to it to get that position, right? Now let's shift our focus to the linked list, right? So here I have a very similar diagram where I am trying to visualize the memory addresses. The first thing you'll notice is when it comes to our linked list being stored, the items of the linked list don't have to be next to each other, right? So here I have some breaks to represent that these chunks of memory that I use up actually don't follow a particular pattern. They could be scattered anywhere through my computer's memory. If I look at a particular unit in my linked list, I'll refer to it as a node. Within a single node, I actually store 2 pieces of information. Of course, I store my value that I want to keep, as well as a reference or a pointer to the next node in the linked list, right? So what I have over here is really like a reference to another memory location, right? So what I can say is my very first node of my linked list is at address 7 in memory, and it contains the value of A. And the second node, or the next node, would be at address 16. So if I jump to address 16, here I have my B node, and it's telling me that its next is at address 20. So I jump to 20, and I have its C node. Next is address 42. Here I'm at 42. Its value is D, and D is actually the last node in my linked list, let's say. Very similar to our array example, which means that its next can be set to null, right? Just to programmatically represent that this is the final node in my linked list. So again, key thing to recognize is that these nodes can be stored at really any random addresses, right? They don't have to be next to each other, right? There's no pattern into how I spaced out these addresses. They don't even have to go in increasing order. The really cool thing about a linked list is if we just maintain a reference or a variable to the very first node of the linked list, we usually refer to it as the head. If I maintain a reference to the head of a linked list, then that actually gives me access to all values within the linked list. I could just reference the next pointer or the next property to get the subsequent node of the linked list. So let's start comparing these two data structures in terms of some fundamental operations. Let's start by comparing how they access values at different positions, right? So let's say the operation I'm speaking about right now is, given some position, return me the value, right? So in my array, I can ask a question like, give me the element at position 2. So that would be 0, 1, 2. That would be the C over here. In a similar way, I can ask for the value at position 2 of my linked list, which would still mean this C value over here. So when you create an array variable, what your computer does is actually just track the starting address for the array. In other words, it's going to track just the address of the very first element, the element at index 0. So if I create an array variable, my computer is going to remember that, hey, the A is at this address, this memory location, we call it 7. And so if I ask for the array at index 2, all it has to do is take this address and then do some arithmetic and find the address 2 spaces later, which is just some math, right? 7 plus 2 gives me 9. And then I know that my value that I should get back is inside of this box, so it's just the C. So in the case of accessing a particular position of an array, it actually operates in constant time because all you do is some really basic arithmetic with the memory addresses. Now let's compare that accessing in linked lists. So a linked list is similar in that when you track a linked list, you're really just maintaining a reference or a variable to the very first node of the linked list. You're maintaining a reference to the head of the linked list. However, in the case of a linked list, there actually is no pattern into the memory addresses for each of these nodes, right? They're basically just random memory addresses. And so I can't just do some simple arithmetic to quickly figure out that, hey, my C node is at address 20, because there's no real reason or pattern to why it's at address 20. It's just random. What I'll have to do instead is just actually manually travel through my linked list. So I start at my head node. And it tells me that, hey, the node at position 1 is at address 16, so I go to address 16. Then I see that the node at index 2 must be at address 20, so I jump to address 20, and there I actually have my C value. So in the case of accessing things inside of a linked list, if you want to access a particular position, you actually have to do O of n steps, or you have to manually travel through nodes of the linked list. Potentially, in the worst case, you travel all the way through the entire linked list, right? However, in the case of an array, when you access a single value at a position of an array, that actually runs in constant time because it's just some simple arithmetic. So if we're concerned about positional access into our data structure, it is a case that a linked list is slower, right? A linked list is O of n, whereas an array is O of 1, it's constant time. So then what advantages does a linked list really have? Well, for one, the fact that a linked list doesn't require a continuous memory, that's actually a huge upshot, right? So let's say that we're dealing with an array. It could be the case that our computer's memory is about full, and maybe there actually are about 4 open addresses in our computer's memory. However, just having 4 addresses is not good enough. If you want to store an array, you need to make sure that those 4 addresses are right next to each other. And that's not actually something that's guaranteed. And so over time, you can imagine that different applications are allocating and deallocating different chunks of memory all throughout. And so over time, things can get very fragmented, right? It's not guaranteed that we'll have consecutive chunks of memory to use for things like arrays. A linked list overcomes this shortcoming because it doesn't require consecutively free pieces of memory, right? It just requires about 4 units of memory overall, so anywhere those memory units lie, we're happy to store our linked list, and things are all good. Let's talk about another operation in which these two data structures differ, and that would be in their insertion operation. So let's say for both of these analogous data structures, I wanted to insert a new element at like the second index. So I want to insert basically an element right over here between the B and the C, kind of in both scenarios, right? So if I wanted to insert a new element at this position for my array, I would still need to maintain the fact that, hey, all of the elements of my array need to be contiguous in memory. So that would basically mean that I have to insert my new element at address 9, and I would have to shift over all of the other elements that come after that position over one address, right? Here's how we should visualize that scenario. Again, I'm inserting X at the second index of my array. You see that the X actually takes that C spot, right? So here it is at address 9, and then C has to move over one position to 10, and D has to move over one position to 11. And all subsequent positions that come after the X have to actually be shifted over. That's a very costly operation. In the case of insertion into an array, in the worst case, that's going to would be O of n, right? Imagine that you wanted to insert a new element at like the very, very first position of an array. You would have to shift over the indices and the addresses of everything in the list. Now let's see how that insertion operation differs for linked lists. So let's say I had a linked list of the same shape, storing the same values, and I wanted to do the same thing of inserting my new value of x right into the index 2, right? So basically between the B and the C when it comes to the sequence of my linked list. The first thing that's nifty about a linked list insertion is that the memory location or the memory address of your new node can be really anywhere. So let's say that a computer happened to have a free address at address 60, right? So that's going to be where I store my x value. How do I actually do the insertion? Well, if I want this x to appear after the B, I just need to correct this B's next pointer, right? So instead of B pointing to C over here, right, at address 20, I'm going to reroute things and say, hey, the next thing after B needs to be address 60. So now B actually points all the way over here, right? And now this X is going to say that, hey, my next is going to be address 20, which means that the thing that follows X is going to be this C. Right? So I actually only need to change one address to insert something into my existing linked list, right? I really just changed this address from 20 to be 60. And notice that my new node has a next address of what B used to point to, right? So I still have the full order of things in my linked list. As you can see in the case of my linked list, I don't have to do any O of n operation when it comes to like shifting addresses, right? I only need to adjust only a handful of different addresses. So overall, in the case of a linked list, insertion is actually traditionally considered a constant operation, so O of 1. So to recap some practical differences between linked lists and arrays, let's take a lay of the land. So when it comes to accessing a value at a particular position, an array is actually going to be faster, right? An array is constant time. A linked list is O of n time because you have to traverse from the head to your given position. But for the sake of insertion and also deletion, because of the same argument, an array is actually going to be O of n, while a linked list is going to be O of 1, right? In the case of deletion, you will still have to do the shifting of addresses for an array, right? So hopefully now you can see how the link structure in a linked list really affords us all of the efficiencies when we compare it to another sequential data structure like an array, right? The fact that things are chained together does give us some advantages. Moving forward, I think a more compact way to actually illustrate a linked list would be the following. You've probably seen a diagram like this before as well. So we don't need to actually represent the different memory addresses. A nice abstract way to represent a linked list is just to have some arrows to the different nodes. So obviously A is my head node over here, its next is B, B's next is C. D actually points to nothing because it's the tail of my linked list. We refer to this simple structure as just a singly linked list because there is a single pointer between nodes that just goes from one node to only its next, right? So a key thing to notice here is, let's say I'm at the B node, there actually is no way that B can reference A, right? B does not have a pointer to A, it only flows downward through the linked list. That being said, there are a few variations when it comes to linked lists. A very common one is a doubly linked list, which just means that every node has a pointer to its next. So B's next is C, but also has a pointer to its previous, right? B's previous is A. And all that does is really clean up the implementation, or really just the code that does operations like insertion and deletion, right? When it comes to the efficiencies, like the time complexity and space complexity of your different implementations, a doubly linked list isn't really more like efficient in terms of big O compared to a singly linked list. It's really just a nice spin-off. Another spin-off of linked lists is the dummy head linked list, which is basically just a linked list where you actually have like a placeholder node to always represent the head. The reason you may want to implement this dummy head pattern is really if you just want to ease the code implementation of operations, right? So even if you had a linked list that was empty, that is, it contains 0 values, technically it would still have one like fake node within it. This means we don't have to handle any edge cases where the linked list is empty, because technically there would always be at least one node under the hood. Both dummy linked lists as well as doubly linked lists are not any like faster or more efficient than singly linked lists. They really just have different code implementations that you might prefer. With that being said, I want us to implement a singly linked list together. So let's jump in. We'll do this in JavaScript. So what I'll start to do is maybe implement this linked list in a somewhat object-oriented way. We know that a linked list contains many nodes. Let me start by actually just creating a nice node class. So nodes are pretty straightforward to implement in any linked list. You just need to contain certain properties. For us, we're going to need to initialize a node with a value. So that's like the stored value that I really care about. But I really need two pieces of information within my node. Of course, I'm going to take that value, but I also need a reference to the next node sequentially. So I think by default, I'll just initialize every node's next to maybe just be null, right? And I'll have to manually reassign that reference to the next node sequentially. So this is a really fundamental node class. I think most of your implementations of linked lists in any language you do are going to have these two properties. Cool. But let's get into the meat and potatoes of this. Let me start defining maybe my main class to actually hold the entire linked list. So I'll create my linked list class. We'll create a constructor as well. Like we mentioned previously, the really important thing to kind of track for a linked list is really just going to be the very first node, right? That initial node, which we refer to as the head, right? Because if I maintain access to the head, then you also maintain access to the entirety of the list, right? Because if you have access to the head, you can just keep flowing through those next pointers to grab every value in the linked list, right? So by default, I want to create like an empty linked list. So what I'll do is I'll set this.head equal to nothing, or rather null programmatically. So here I have my linked list class. Let's start to give it the ability to just add nodes into my linked list. So we'll keep things simple over here. Let's say for my linked list, we'll have a method that always adds a new node to the end of my linked list, right? So I can add things sequentially. In other words, let's say I created an instance of a linked list and I did something like list.append and I appended the value A, and then afterwards I appended the value B. I think like the visual representation of this linked list should be something like A points to B, right? So whenever I do append, it will always add like a new tail to my linked list. So let's start by doing that operation. I'll call it append. Notice that I'm not going to do a full insertion here, right? So I can't insert like anywhere in the middle right now. I'll probably save that for you guys. But for my append method, what should we do? Well, I know that I have this kind of edge case when I insert the very first node into my linked list, right? It could be the case that I'm inserting for the first time, or rather appending for the first time, which means that my head is set to null. So I need to make sure that I assign something to head. That way I can maintain the entirety of my linked list. So I'll handle that pretty explicitly. I'll just check, hey, if there's nothing in my linked list, which programmatically means if my head is null, then what I'll do is just create a new node and I'll be sure to assign this.head to that new node, right? So I'll create an instance of my node. And I should be appending with some value here, right? So this is like my stored value. Create a new node with that value and make sure it's set as this.head. Cool. And after I do that, that would actually be the entire initial insertion, right? So I can just do an early return over here. So it's really important for your linked list that you handle your edge cases. The most apparent edge cases, of course, have to do with having like an empty list. So this will handle my very first append into my linked list. But now let's handle the generic case, right? If I have at least a head, so if I have at least one node, then appending is a little more involved, right? So let's say that my current linked list contains two nodes, right? If I wanted to insert a new node C, I know that I actually have to travel through my linked list, right? So I already have access to the head of my linked list, which would be the A node over here. But what I need to do is travel. So what I can do is take this pointer and actually shift it to A's next. So what's A's next? That would bring me to B. Then once I'm at B, this is actually the perfect spot where I can add my C node, because I can just set B's .next to be C. And this pattern actually follows no matter how many nodes I'm adding into my list. So let's say I appended now a D node. I would just have to travel a little farther when it comes to this diagram, right? So let's say my current linked list had values A, B, C. What I should do is, again, start some variable pointing to the head of my linked list and keep setting my current location to current.next until I'm at the tail, right? So if I get A's next right here, that would give me B. If I take B's next, that gives me C. Since C has no next, I know its next is null, which means it must be the current tail. So I can just insert my new node over here, and all is well. Let's actually code that up together. It's actually not too hard of some code. So here's what I'll do. After this kind of handling of the edge scenario for my empty list, let's start our generic case. So I'm going to need a variable to track my current location. Traditionally for linked lists, we call that cur. Stands for current, and I'll initialize that with this dot head. And now what I want to do is keep traveling through the linked list until I hit the tail, right? So I can just use a nice while loop here. Over time, I'm going to be reassigning this current, right? So I know in general, I want to keep looping while my current dot next is not equal to null. So what does that mean in English, right? If I look at this while loop, this says keep looping until you hit the tail, right? So once current.next is null, then I'll exit this loop, which means that current must be the tail, right? And so to actually have this code work, what I need to do is keep reassigning cur. So I can say cur equals current.next, right? So take my current node, but then set current equal to its next, right? So for example, if I'm at A and I do current equals cur.next, then I'm setting current to really be B. I'm going to do that for C. And this will stop once current points to the tail, right? So to me, after this while loop is done running, that means kind of right over here, that means that current is the tail, right? So all I need to do is set current.next to be a new node. So I could just steal this code over here. Right, to add a new node at the very end, just take the tail and set its next to be your new node. Cool, and it is the case that this new node already has its next as null, so it's okay to act like the tail. Cool, so this code is looking pretty good. Let's actually test it. So let me just try running this code. Obviously, I don't have a nice way to visualize things quite yet, but we can work on like a nice print method next. So at least I get no errors. Let's start by maybe console.logging, and I'll console.log list.head. So I'm printing out my linked list head, which would give me like the A node. So let's just see if that works. So I'll run this file. So yeah, list.head is definitely the A node, right? Its value is A. If I look at its next property, it actually points to another node whose value is B. And of course, B's next is another node whose value is C. And it looks like when it comes to just my JavaScript runtime right now, it's not going to keep nesting the output over here. But if I had to guess, like this next reference for C would actually contain the D node. But let's actually be sure of that. So what I'll work on now is a very simple method that just prints out values in my linked list. Let me zoom out a tiny bit. And so now that I have this append method, I need a way to visualize things. I'll just call it print. Nothing too fancy over here. And here's what I'll do. Let me start by defining this method, and I'll actually use basically the same pattern. So I already know that like this code more or less just like travels through my linked list. So I'm going to actually use that pattern over here. So I'm going to start with my cur pointer set with this dot head. Now I want to actually change the while loop, right? So here I'll actually run my while loop by saying, hey, while current is not equal to null. And what's the reason for me kind of switching things up over here? You'll notice that in my append, I checked if current.next is not equal to null. Whereas here, I kind of dropped the .next. I'm just checking, hey, is cur itself not equal to null? Well, since I'm just printing over here, I actually want to loop even through the tail node, the last node of my linked list. And another upshot of having this particular while loop is that it will automatically handle the case where the head is null, right? So let's say that my list is empty. That means this dot head is null, which means current is also null, which means this while loop is checking, does null not equal to null? That actually evaluates to false, so I won't even enter this while loop. So this is actually a nice concise print I can use over here. And all I'll do for this one is maybe concatenate some things together. So let's say in my print method, make this a little fun. I started out with some string that's empty. And as I loop through like every node of my list, what I'll take is my string and maybe add to it the current value. So I'll take cur.val. But of course, I still need that pattern to actually traverse to my next node after I'm done with this iteration. So I'll steal this line as well. So this pattern of like cur equals cur.next is very characteristic of linked list algorithms, right? So over time, I'm looping through the entirety of my linked lists and just taking the value and concatenating it to my string. So let's go ahead and save this. And after my while loop, I'll actually console.log that string. So that should just print out all of the values in order. And now over here, I'll just do list.print. That should print out A, B, C, D. So let's give that a shot. Cool, here I get A, B, C, D. Maybe just to make it a little more clear, whenever I add a value into my string, let's also just add like a little arrow, make it a little nice. So let's see that. There I can start to see my linked list. Notice that D's next over here is indeed going to be set to null. So I think let's trace through how this print method works, because this pattern of like a while loop that just travels through a linked list is probably the most common pattern that you'll always use for a linked list. So when you trace through your programs, it's important to track your variables that are important. And it's usually going to be the variables that change over the runtime of your code, right? So if I'm tracing through this print method, I'll track my str variable. It's going to be the string I accumulate over time. That starts empty, so I'll leave it blank over here. And I also need to track this cur variable, right? So I know that cur begins at this dot head. I know that since I've added A, B, and C, and D into my linked list, that means that this dot head would refer to this particular node over here. So this arrow down below would actually represent my current location, right? Cool. So what happens? So cur is pointing to this A node, and I check, hey, is that A node not equal to null? And that's actually true. So I do get to run the code inside of my while loop, which means I take that node's value. So I take A, and I just add it to my string over here. And then what I do is I take my current pointer and set it to current.next, right? So remember that cur is really this arrow over here. If I set cur equal to cur.next, what's A's next? Well, it's just B. So that means my new cur is actually over here. Right? And that brings me to the end of my first iteration. So now I'm back at the top of my while loop. I'm at my B node. Is the B node not equal to null? That's true. So I can just add B into my string. So I'll just not put the arrows over here. And then I take B and set it to B's next. So now my current location is C. Same thing happens, right? I'm still not null. So I can add C into my string. And then I can set C to C's next. So I'm at D. And things start to get interesting about here, right? D is still not null. So I can add D into my string over here. And then I can set D equal to D next. You notice that D's next is actually going to be null right now. So technically my cur pointer would actually be pointing at like nothingness, so the null value. And then I check, hey, is null not equal to null? That's actually a false statement, which means I exit my while loop and just print out my string, which contains the values A, B, C, D. Awesome. So that's a really core pattern when it comes to linked lists. And basically, with just this like while loop pattern in mind, you can implement so many different linked list operations, right? So let's say I wanted to add one final method into my linked list, right? So I know my linked list contains A, B, C, D. It would be awesome if I could check for existence into my list. So if I did something like list.contains, I want that to return a Boolean, right? So if someone did list.contains A, I think that should obviously give back true. If someone did B, that should give back true. And basically for A, B, C, D, all those values are inside of my list, so they should all return true. Now, if I looked for something that was not there, I don't know, like a Z or even like an X, those should actually give back false, right? So a very, very straightforward Boolean method that just tells me, hey, whether or not my list contains that particular value, right? So I want to actually implement this contains method is really just a short spin-off of this print method, right? So let's start defining it over here. Let me start by saying contains as an instance method. And I will definitely need this pattern of just iterating through my entire list. So I'll steal this code, still need that while loop. And I still need to, of course, travel through my linked list. So important thing to always remember is you set cur equal to cur.next. So far, this while loop alone gives me logic that steps from one node of my list to the next. But how can I actually meet this spec now, right? What I want to do is check the value. In particular, I can check, hey, if my current node's value is the value I'm looking for, then I can return true. So let me add an argument into my contain. So look over here, right? I should pass in some value to check. So I'll say this is my target. So if my current node's value is the same as my target value, then I've just found the thing, so I can verify that it's there. I can return true, right? So an early return true as soon as you find the value. Cool. And now the question is, where should you return false? Well, you should only return false after you checked the entirety of the linked list. So that means I should return false after my while loop is done traversing through every node. So if ever you finish the while loop, that means that you never found the value you're looking for, so you never return true, which means that automatically I can return false because it is exactly the case that my target is nowhere to be found inside of my linked list, right? So this is a very, very straightforward method. Notice how it just like incrementally builds on top of this simple like traversal pattern. So let's save this code and I'll go ahead and run these cases for contains. So if this works, I should get 4 trues and 2 falses. Let's give it a shot. Nice, and there's our valid output. Cool, so those are some fundamental operations when it comes to dealing with your linked list. I feel just by implementing a very simple linked list, you actually basically unlock so much knowledge about a bunch of linked list problems that you could encounter on your software engineering interviews. A few things I want to bring up when it comes to the values you store in a linked list. Of course, they can be anything, right? So if I wanted to, like, I can append on like a number like 42. I can just check, hey, is 42 within my linked list, right? You can store really any information you want in a linked list. It can even be like another object, right? So I should get a true for this last print over here, right? You can mix up your data and store anything if you so choose. You can also totally store like duplicate values in your linked list. It really doesn't really matter, right? So here I can have D appended twice into my linked list as well. So let's say I printed out my linked list with this D being duplicate. Notice that I can still see it just fine. The main characteristic of a linked list is that it is sequential, right? So there is an order to the values in the linked list, right? So I can say things like A is the first value in my linked list, whereas D is the last value of my linked list. So there you have it. There's your introduction into a linked list. What we did today was implement a singularly linked list that supports basic methods like appending a new value to the end of the linked list, printing out all values of the linked list, as well as checking for existence of a value within that linked list. In the next video, I'll show you how to implement a linked list with recursive methods.